Hi everyone. Today's devotional is from Isaiah 26. We have a strong city. God makes salvation its walls and ramparts. Open the gates that the righteous nation may enter, the nation that keeps faith. You will keep in perfect peace him whose mind is steadfast because he trusts in you. Trust in the Lord forever, for the Lord is the rock eternal. So obviously we're talking about membranes, and so this kind of made sense to me because we have a membrane component here. God's our protection, and membrane is protection of the cells and so forth. But really, I think God, in the meaning in this scripture, goes well beyond that. God basically protects us inside and out. But if we keep ourselves righteous and we keep our minds focused on God, then we're going to protect ourselves from sin and other things as well. You will keep in perfect peace him whose mind is steadfast because he trusts in you. God trusts in us. That's pretty cool. Trust in the Lord forever, for the Lord is the rock eternal. The Lord is the only real solid foundation that we have in life. And if you keep that in mind, it kind of makes everything else obsolete. And that's not me or the Bible or anyone saying that there aren't a lot of things in life that are important. Certainly family, certainly church, certainly education, all kinds of things are important. But ultimately, it all rests on God as the foundation, as the protector, and as the salvation. And so keep that in mind, and I hope that has some meaning to you and some reflection. We talked a little bit in our introduction to this unit about why it's important for the membrane to have fluidity. So we need that membrane to be quite flexible so we can have vesicles protruding out and vesicles fusing with the membrane, also so we can have cell movement, all kinds of things. But it can't be too completely fluid because then that basically would mean our cells are just kind of washing out. The membrane, it needs to have some structure and some protection so that it separates the inside to the outside. So what are some things that affect membrane fluidity? Well, the first factor that affects the fluidity of your membrane is temperature. And this one is relatively obvious. We know that as things get cold, they're going to get more solid. All right, so if you're freezing water, the colder it gets, the closer to frozen, and by the time it's frozen, it's very solid. Whereas when things are warm, they're going to be more fluid. And so the transition temperature is simply the temperature at which the membrane becomes frozen. So that's the transition between some fluidity to completely frozen. And if your cell is frozen, basically you're dead. So this is something that can be really detrimental, obviously. So temperature can very much affect membrane fluidity, but there's a lot of things cells can regulate to counteract that and to make sure that they maintain the correct level of fluidity when things are too hot or when things are too cold otherwise. What are some other things that affect membrane fluidity? Well, the composition of the fatty acid tails. All right. So unsaturated are going to be less tightly packed and saturated are more tightly packed. And you've heard about this before. So if you have your phospholipid head group and you have saturated fatty acid tails, those saturated fatty acid tails are straight, whereas an unsaturated fatty acid tail is bent. And so if you have a membrane whose phospholipids have a lot of unsaturated fatty acid tails, those phospholipids are going to be further apart from each other. And the further apart, so if we have unsaturated, they're further apart, and that means they're more fluid. You can think about this because if you're trying to pack something and you have a bunch of things that you're trying to pack together that are kind of round or they're not this kind of square box-like shape, it's harder to pack as many of them in there because the round shape is kind of pushing away. Whereas the saturated tails, those are very straight. And so those straight tails can pack tightly together. So pack tight, and that means that is less fluid. And here we can see this well. So here's a membrane, phospholipid bilayer, that's full of just saturated, and these are nice, tightly packed together because they're nice and straight. Here we have an unsaturated membrane, and you can see that those kinks in the fatty acid tails are basically pushing out, and being further apart means that they are more fluid. All right, so unsaturated makes them more fluid, saturated makes them more viscous or more tightly packed. And when we take a look over here, we can see that these are just 3 common fatty acid tails. Here we have, I don't know why this turned on the side, but here we have stearic acid. So stearic acid is our saturated one, very straight. Here we have oleic acid, all right, so that's bent, but just a single, this is monounsaturated, so that single one causes a bit of a kink, but oleic basically has 2 double bonds, and immediately this is almost takes more than a 90-degree turn. So you can imagine that those polyunsaturated fatty acid tails are really going to push out that membrane and make it more fluid. All right, what else can affect this? Well, the distribution. So believe it or not, if you have a membrane that has 1 fatty acid tail on each phospholipid, all right, so basically 1 is saturated, 1 is unsaturated, saturated, unsaturated, and so forth. If you had that same membrane with 4 fatty acid tails, all right, so here we have our phospholipid head group, and I'm going to put 2 unsaturated on this one, but then I'm going to put, or sorry, that's 2 saturated, then I'm going to put 2 unsaturated on this one, and 2 unsaturated on this one. Basically, even though we still only have 4 unsaturated chains on both of these, by having the unsaturated fatty acid tails on the same phospholipid, things actually get pushed out even further. Even if you have some phospholipids that are pretty tight in here, these ones that are interacting with both of those fatty acid tails on the same one, that pushes things out. All right, so in summary, what we have is that evenly distributed unsaturated fatty acid tails basically is going to be more solid than ones where multiple unsaturated on the same phospholipid, and that is going to be more fluid. All right, one more important one. The length of the fatty acid tails. So if you have a shorter set of fatty acid tails, and we're talking about the length now, that's going to become more fluid. So why? Well, let's think about this. We have our phospholipid bilayer, and it's the hydrophobic effect that's basically keeping these this membrane in this structure because those fatty acid tails are trying to get away from water. However, those fatty acid tails, they are interacting with each other, but not through anything. There's no hydrogen bonds in there. Remember, these are non-polar. There's nothing like that. What's interacting is van der Waals. So we have van der Waals interactions, which basically means that anything with any mass at all, even tiny little molecules, they are going to have some attraction together. So that is preventing this from being completely fluid, because for a while this phospholipid is going to interact with this one with some van der Waals, and it takes a little bit of effort to pull that away, but it's just as happy interacting with the next one, and so we still have that really rapid fluidity that we've seen before. However, we cannot negate those van der Waals, especially across an entire membrane, because across the trillions and trillions of phospholipids on the membrane, they have some significant interaction. So, which ones are going to have more van der Waals side to side? If we have shorter fatty acid tails, or if we have longer fatty acid tails? Well, the longer the fatty acid tails are going to have more van der Waals. And if they have more van der Waals, they have more interaction. And that means they're going to be stuck next to each other a little tiny bit longer, and that's going to make it more solid. The shorter ones, on the other hand, less van der Waals, and that makes them more fluid. All right, so let's kind of think about this a little bit further. Oh, sorry, one last thing that really is important for this, and that's cholesterol. Cholesterol, I tend to think of as antifreeze. Now, antifreeze, obviously, if you use it in your car, prevents your car from freezing. But antifreeze also prevents it from overheating. All right, so it kind of prevents both ways. It prevents freezing and it prevents overheating. So in other words, what this means is it's going to moderate fluidity. That's the role of cholesterol. So in other words, cholesterol is going to keep the membrane from freezing at really low temperatures, but it's also going to keep it from being too fluid at high temperatures. So it prevents freezing, but it also prevents too much fluidity. So what it does with regards to making it the membrane more or less fluid really depends on the temperature, because it just keeps that fluidity moderate in the middle. Why is that? Well, this is cholesterol. And cholesterol has these 4 rings. And if you have rings, that is a very rigid structure. Fatty acid tails themselves are these floppy, kind of long single carbon-carbon interactions. And so these are actually very floppy. They're constantly moving, they're rotating around, they're moving. But these cholesterol molecules with their rings are not moving nearly as much. And so if you have movement in the fatty acid tails, that movement is affected by temperature. In other words, at cold temperature, it can stop moving a lot. At high temperature, it moves a lot more. So these fatty acid tails, the fatty acids of phospholipids, are highly affected by temperature. But cholesterol with its rings, you can cool that off and those rings aren't going to change their structure very much. You can heat it up and those rings don't change their structure very much. So cholesterol basically moderates the temperature. Sorry, not the temperature, but the fluidity and the effect that temperature has on fluidity. So, one of the ways that our membrane stays regulated is because we're warm-blooded. We can actually regulate our body temperature so our membrane shouldn't get way too hot or way too cold. However, there's a lot of organisms out there that basically are not warm-blooded, and so their membranes are going to be largely affected by the environment, including bacteria. So what can these cells do to help prevent that membrane from freezing or becoming too fluid? And the things that these non-warm-blooded organisms can do are actually the same thing that our cells do. Our cells just don't have to do it quite as drastically because we are warm-blooded. What are some of these changes? Well, they can actually affect the saturation. So they can change the saturation levels. And there's actually desaturases. These are enzymes that desaturate the hydrocarbon tails. So what would those do? What would desaturases do? Well, if they're desaturating, they are going to make more unsaturated, because they're taking a saturated one and making it unsaturated. And so that's going to make it more fluid. There's actually saturases as well. And that's just going to do the opposite. It's going to take an unsaturated fatty acid and saturate it, and so that's going to make it more solid. All right, remember how I said if you have both of your unsaturated fatty acids versus kind of evenly distributed, that also makes a difference. So there are enzymes called phospholipases that can break off a fatty acid tail and then redistribute it onto other fatty acid tails. So the phospholipases break off the fatty acid tail, acyltransferases transfer them and reshuffle them so that you can create phospholipids with 2 unsaturated chains on the same one, or you can basically start to make them evenly distributed where each phospholipid only has 1 unsaturated chain. All right, and then there are enzymes who actually can alter the lengths. And we now remember, hopefully, that the shorter fatty acid tails are going to be more fluid because there's less van der Waals interactions. I have no idea what this enzyme is called. I don't even know if it has a name. I've looked it up many, many times, so I am just going to name it. We'll call it fatty acid shortase. So fatty acid shortase is my made-up name of the enzyme that reduces the length of the fatty acid tails. But this is how the poikilotherms, the ones that can't regulate their body temperature, how they regulate membrane fluidity. And then our cells also can regulate membrane fluidity by altering the levels of cholesterol in them. Remember, cholesterol is kind of that antifreeze. All right, so hopefully at this point you understand what factors affect membrane fluidity and how cells can regulate their membrane fluidity by altering saturation, altering the distribution of those saturated and unsaturated fatty acid tails, and by altering the length and playing around with the amounts of cholesterol. All right.